Hello, and welcome to Science Journeys, Caltech's first online science education series. I'm Michael Alexander, the director of Caltech's public programming, and I'm very happy to have you all with us today. Caltech is one of the nation's premier science education and research institutions. In fact, Caltech created the Jet Propulsion Lab, JPL, which has managed most of the United States' unmanned space flights. As we speak, there is an unmanned space mission on its way to Mars that includes a helicopter that will be the very first to ever fly on another planet. Our office is also responsible for bringing to the campus the Performing Arts series that takes place here in Beckman Auditorium. We would encourage you all to look to our website, where you can find out about all of the lectures and performing arts series that are going on here by going to events.caltech.edu. Today's speaker is Jake Evans. Jake Evans loves being a chemist. He gets excited every time he gets to talk about it. Jake is going to tell you about how chemistry is involved in every aspect of all of the other sciences. You're going to hear about the difference between energy and power, and a number of other facts, including how energy that we are using today is compared to the energy that was being used decades ago. He will be talking about how we're getting a chance to use solar power, and some of the challenges that we are still facing are the challenges that we hope some of you will be taking on as you get into the sciences yourself. So now, it gives me great pleasure to welcome to the stage, Jake Evans.
Thanks, Michael. Hey everyone, I'd like to welcome you to my talk on fueling the world engine, which I hope will make a lot more sense to you at the end of this talk. My name is Jake Evans. I'm a first-year chemistry PhD student here at Caltech, and I'm really excited to be giving this talk to you here today. But first, before we get into the science, I think introductions are in order. Hi, I'm Jake. That's me there when I was really young. I've kind of always been interested in science. You can see me there mixing up some sort of thing in my backyard. But I did all sorts of fun little projects, but science was always an interest of mine more than a career until I got a little bit further in my education. So I'm originally from North Carolina. I went to public high school, Fuquay-Varina High School, right about there. And then when I went to college, I went to, again, a public college not too far from there, University of North Carolina at Chapel Hill, which is right there. Once I was there at UNC, that's where I really started to develop science as a career. I got involved in a laboratory. You can see me there in my lab coat. I was also able to do more science communication. So here I am. I actually worked at a planetarium for a while there. And that's where I started to meld this idea of being a researcher and being a communicator, because I really enjoyed doing the science and trying all these experiments, but I also really enjoyed talking to you. So I was able to put that together a little bit. So I've got a little picture of me here doing a presentation. This one was more of a formal scientific presentation I gave when I was an undergrad. But then it was time to move on. So I came here to Caltech. And one of the things that I did once I got here, in addition to getting involved in research, doing solar energy and corrosion studies, I got involved with this organization called the Center for Teaching, Learning, and Outreach, also known as the CTLO, where I would go into some public schools and talk to people about what I do and talk about how you can do what I do, and just learn a little bit about them, and they can learn a little bit about me and have a little bit of fun along the way. Okay, it's time to get into the science. So what are we going to be talking about today? We're going to be talking about energy, all different types of energy. We are going to talk about the way we use energy now and the way we're going to use energy in the future. We're also going to be talking about chemistry. I'm a chemist, which might surprise some of you. You might be wondering why a chemist is going to be talking to you about energy. You're probably used to seeing an environmental scientist or a physicist talking about this, and you're probably more used to seeing a chemist blowing things up on stage, maybe laughing maniacally over a colorful solution. And don't get me wrong, we do that sort of thing, We do work with dangerous chemicals, we work with colorful things, but we also work with everything else. That's what I love about chemistry, is that it's true that you can find chemicals in these colorful little flasks, but you can also find it in your own body. You and me, we're both made of chemicals. All animals are both made of chemicals and powered by chemicals, but it's not just animals. It's also plants, like that tree there. Rivers, environments are rich in chemistry and are currently being explored by lots of different researchers around the world. Even things like food. It doesn't matter how non-GMO or free-range your food is, it's all chemicals. It has to be. If it's not chemicals, it's not food. And then we can go even further, things that we build with. So I've got a light bulb here, so we can illuminate our world with chemistry. We can build things. We can make steel. We can make it better with chemistry. So there's all sorts of interesting things you can do in this field. So if you walk away with nothing else from today's talk, I hope you walk away with this, that everything is made of chemicals. And that if you're interested in something and you want to get into the chemistry, you absolutely can. Okay, so let's get into some definitions. So I'm going to be using the words energy and power a lot in this talk, and I want to make sure I'm clear with what I mean. So energy is defined as the ability to do work, okay? So that just means that it's the ability to move things around a little bit. So I've got a picture here of a nice gentle breeze flowing over some reeds, where power is the energy used per second. It's a rate at which you use energy. So I've got a picture of an explosion here. And the interesting thing is that both of those pictures have a similar amount of energy behind them. It's just that the explosion is releasing it all at once. It's releasing it much faster. It's much more powerful. Okay? So that's sort of what I want you to think of. When you think of energy, you want to think of the ability to move things. And when you think of power, you want to think of how fast you're doing it. Okay? So we're going to use this idea of the world engine to drive this talk. So just like you have an engine in your car, we're going to imagine that there's an engine powering the entire world. And we're going to ask some questions about it. We're going to ask, how powerful is it? You know, if the car engine, say in my car, is around 200 horsepower, how many horsepower is the engine that runs the world? Then we want to ask, what's the fuel? Like in cars, we know we put gasoline in them, but what do we put in to the world engine? What do we use to power the planet? And then can we use what we learned about this engine to make a better one? Here's just some little scientific graphs for you. So I've got a graph here of the amount of power used by the entire world over the course of a year, up to 2017, which was the last year I got good data for. So you can see that the last entry is about 18 terawatts. Okay, so we're going to talk about what that is. So a watt is a unit of energy, just like horsepower. And so to compare it to horsepower, we're going to look at this supercar here. So that car has an engine in it, which has about 1 megawatt of power. Okay, so that's a very fast car. But about 1 megawatt is what we could think of for this car engine. Mega means a million. So that car has 1 million watts in its engine. But we need to get to terawatts. Now, tera means a trillion. So we need to do 1 million times 1 million. So that's going to be like taking the engine out of that car and strapping 30 space shuttles to it and firing them at full blast. So that's a lot of power, right? And we need 18 of those in order to run our world engine. That's a very, very powerful engine. And to really put this in perspective, if you took 1 million seconds is about 11 days, right? So 1 second is about that. 1 million seconds is about 11 days. 1 trillion seconds is about 31,000 years. So you can get a sense that if we were to fire this car at full steam, it would look less like a car and more like a rocket re-entering the atmosphere. So now we know how powerful this world engine is, around 18 terawatts. Now we need to know how we fuel it. Okay, so when we are fueling our power sources today, it's mostly 3 things: coal, oil, and natural gas. Okay, that makes up about 75% of what we put into our world engine. And all of them use this chemical reaction on the bottom of the slide, where we're combining carbon, and oxygen, and we're creating carbon dioxide, which is a gas, and we're releasing energy. And that energy is what we're harvesting to run our engine. Now, that reaction is called a combustion reaction because the easiest way to combine that carbon and that oxygen is to set it on fire. And that's actually a pretty common thing. If you are going to have a carbon-based fuel, if you are going to get the energy back out, you need to do a combustion reaction, which is going to release carbon dioxide. So just remember, right now, we mostly fuel the world engine with carbon. Now, this can be a little bit of a problem. We've learned in the past few decades that as we increase the amount of carbon dioxide in our atmosphere, we are also increasing the temperature of the planet, and that can make it harder for different species to survive, possibly including us. So one of the things that we've been learning is that it's really, really important that we control the amount of carbon dioxide we put in the atmosphere, because it turns out it is a lot. So the big problem with the world engine is that we're getting too much carbon dioxide in the atmosphere, which is mostly from running our processes. And those processes are mostly from the coal, oil, and natural gas, which is fueling that world engine. So what if we did something different? Okay, so we're looking into a lot of different renewable energies right now. I've got a graph here which shows the amount of power we could get out of each one, and then I've got a little orange line that tells you that's how much power we need to power the entire planet. That's 18 terawatts, and the only one that meets it is solar energy. So we can get a lot of energy out of solar power. And they're mostly out of these things called solar panels, which you might have seen before. If not, I've got right here a little solar panel. So this is just a nice little one, and we can use this to power all sorts of things. And so we've got a little demo to show you how that works. What we're going to see is how it absorbs light and converts it into electricity. So the first thing we're going to do is just cover it so there's no light getting to it, or very little light getting to it. And I'm going to connect it to this device, which is called a voltmeter. It's going to tell me how much electricity is coming out of this solar panel. So I'm going to hook it up, and we should see, about 0.1 volts maybe. There's not a whole lot of electricity coming out of the solar panel right now. And that's because right now it's acting a lot like an insulator. So there's electrons can't move a whole lot. But this time, I'm going to turn on this lamp. I'm going to put the solar panel underneath the lamp so it can absorb the light. And I'm going to hook it up to the voltmeter again. So this time we can see we're producing a lot more electricity, about 1.7 volts of electricity. And that's because those electrons are now acting like a conductor. They can move around a whole lot because the semiconductor has absorbed the light. We're going to get into why silicon works, how these solar panels work, but we're going to need to understand a little bit of chemistry to do that, okay? So what I've got here is a basic picture of an atom. There's three main components. There's protons and neutrons, which form the nucleus. That's at the middle. And there's electrons going around the outside, and that's where the electricity comes from. Now, atoms are the basic unit of matter, which means they're the basic unit of chemistry. If you change the atom, you change the way things react. So if we change away from carbon, we're going to need to think about how different things react. Now, this isn't exactly what an atom looks like. They look a little bit more like this. These are what electron orbitals actually look like, but for our purposes, this understanding is perfectly fine. So there's carbon. We've been talking about how useful it is. We've been using it for a long, long time. It's a great source of energy, but we need something else. Now, silicon is right below it on the periodic table. And if you're familiar at all with chemistry, you might know this, but just in case you don't, if you go up and down on the periodic table, you're going to find elements that react similarly to each other. So you're going to be a whole lot like your neighbors above and below you in the periodic table. Silicon is below carbon, so we should expect it to act very similarly. So carbon can make a lot of bonds. We should expect silicon can make a lot of bonds. And it can. Silicon is an incredibly versatile element. So we've got a crystal structure of it there. You can see it can form all sorts of different bonds. It's also everywhere. So silicon is in essentially every electronic device. So it's in the computer or phone you're using to watch me right now. It's in the camera that's filming me, right? It's all over the place in electronics, but it's also just all over the earth. Sand is mostly, it's silicon and oxygen. So silicon is the major component of sand. So we're not going to be running out of it anytime soon. We've got lots and lots of silicon laying around. It's also something called a semiconductor. So to understand what a semiconductor is, let's start by understanding what a conductor is. So I've got a little bit of gold here. So this is what we would call a conductor. Most metals are. That means that it's really easy for those materials, those chemicals, to move electrons back and forth, which is why we use them in wires, right? We want it to be very easy for the electrons to move around. There's also materials called insulators. So I've got just a piece of rubber here. So insulators are sort of the opposite, where conductors want to take those electrons, remember the outside of the atoms where the electricity comes from? Conductors want to move them around really easily. Insulators lock them down. Insulators do not want their electrons to move at all, which is why we don't make wires out of rubber, because it's really, really hard to move electrons around. But silicon is in the middle. So if you've never seen silicon before, I've got a little bit of pure silicon here. So it's very shiny on one side and not very shiny on the other. This is what it looks like. It is a semiconductor, which means sometimes electrons move around a whole lot, and sometimes they don't. And that's really, really powerful, because we can control when those electrons move around and when they don't. So let's talk about how a solar panel actually works. So I've got a diagram here where we're going to go low energy is on the bottom of the slide, high energy is on the top of the slide. Generally, if you're high energy, you're not very stable. And if you're low energy, you're very stable. Now, there's two parts of a semiconductor. There's this thing called the valence band, which is where it acts like an insulator, where those electrons don't like to move around a whole lot. And that's where the electrons usually are in a semiconductor. They're usually way down in energy, nice and happy and stable, and they're acting like an insulator. They don't move around. But there's also an area called the conduction band, where those electrons can move just like a conductor. Now, all we need to do to get those electrons from the valence band to the conduction band is give them some energy. And the way we do that is with light. So I've got a little photon of energy here. That's a packet of light energy. And we're going to shine that light onto our solar panel, where it's going to get caught by our electron, which I've represented here as a car, because everything in this talk is represented by a car. And it's going to absorb that energy and go up into the conduction band. And now that it's in the conduction band, it can move around very easily. And it can fly all the way off into the wire or into the grid or wherever it needs to go. Okay? So that's how a solar panel works. They're just semiconductors, and what we're doing is putting energy in to move the electrons up in energy, which we can then use to power all sorts of things. Okay? There's a problem, though. So I've got a picture here of Los Angeles at night, and there's two things you should probably notice about this. The first thing is that there's a lot of lights on. Now, it turns out that we use the most power at night, which sort of makes sense if you think about it. That's when we turn on all the lights, right? So we use a lot of power at night. In fact, we use the most power at night. But there's another thing. Do you see the sun in there anywhere? No, right? The sun goes down at night. That's what makes it nighttime. So that means that solar panels don't work at night. We can't pull those electrons up in energy to power all those lights if we have no sun. So that means we need to store the energy. And that is one of the big problems facing chemists today. Our job, and maybe your job someday in the future, will be to find a way to capture the light of the sun, probably using some kind of solar panel, just like we were talking about before, and then we're going to store it somehow. Right? We're going to see if we can find out a really good way to store that energy. And as long as we're going to find a good way to store energy, why don't we ask nature what it does? Because in case you didn't know this, leaves are a lot like solar panels. It sort of makes sense if you think about it. Solar panels are big and flat and wide to catch a whole lot of sun. And so are leaves. They're big, flat, wide. They catch a whole lot of sun. And I've got a little demonstration for you here where we can see what is going to happen here. So I've got a jar here that's got some leaves that I just picked a few minutes ago. A little bit of water in there. And then I've got another jar. This has something called iridium in it. This is a man-made chemical that can do something sort of similar to what a leaf does. So what I'm going to do here is I'm going to move these out of the way, and we're going to shine lights on them. And as we shine the light, they're going to start doing a chemical reaction, and we're going to capture what they make in these little tubes here. So I'm going to get these out of the way and start that reaction going. Been a few minutes now, and so let's check on the progress of these leaves and that iridium, and let's see how much gas they've made. So the lights have been on for a while, so let's turn these off, and let's pick up our jars, just like that. Okay, so in this jar, we had the leaves. So we have the tube leading up here. And you can see that we've displaced some water. Looks like around a milliliter or two. And all of that is the gas produced from this reaction. In this case, it's oxygen. So this is pure oxygen gas in here. And you can see this is the best human stuff. This is iridium. This is one of the best man-made substances for making this oxygen. And you can see over the same amount of time, it's not producing quite the same amount. Nature is very, very good at what it does. But we're still getting around a milliliter of gas, which is quite good over just a few minutes. But this here is part of the problem, is we're trying to learn how to do these reactions better so that we can do as well as nature and then maybe one day do even better. So one of the things that we're going to learn about nature is that nature figured out a way to do this. Nature has already solved this problem for us. So what nature does is it takes that sunlight, absorbs it with its leaves, which we just learned are like solar panels, and then it stores it as a fuel. In this case, the fuel is sugars. In fact, sometimes it's literally sugar. So if you've ever had regular sugar, it's called sucrose, and it comes from sugarcane. So what happens there is a plant literally turns sunlight into sugars. Now, different plants will do slightly different reactions, but they're all going to be making a fuel, and usually in the form of a type of sugar. So how does a fuel work? Right? We're going to be storing this energy as a fuel, which is what the plants do. So what a plant does is it performs two reactions. One is an endothermic reaction, which means it's going to take energy to push this reaction up, just like we were doing with that solar panel. So I've got a carbon dioxide molecule, and the plant is going to take that sunlight and that leaf, and it's going to push it up in energy and transform it into sugar. So once we have it there, you can see it's sort of in a valley. And just like if you were to have a ball sort of sitting in a valley, it's not going to want to move. It's nice and stable there, even though it's higher in energy. So this is how we store energy. That's what a fuel is. It's a molecule, in this case a sugar, that is high in energy, but stable enough that it can hold on to that energy for later. So that's exactly what we're looking for. We're then going to perform another reaction, in this case an exothermic reaction. I'm going to do a combustion reaction. We're just going to set it on fire, where we're going to release all that carbon back from the sugar, release all of that energy, turn it back into a molecule of carbon dioxide. So that's our goal. But you notice the plants are still using carbon dioxide, and we really want to avoid that, right? We want to make sure that we're putting less carbon into the atmosphere. So maybe we can do a little bit better. So I've got a graph here of the amount of energy that each different type of fuel can store. So we've got sugars, which are not bad. They've got a pretty good amount of energy per amount of mass. But the first thing you might think of if we're going to be storing energy is a battery, right? We use batteries to store power all the time. That's the way that we are able to use our phones over and over again without plugging them into the wall. So let's look and see how much energy we can store in a lithium-ion battery. Turns out not very much. Lithium-ion batteries are not that good at storing energy. They work fine for most applications, and there's lots of people doing great work making new batteries. But for our purposes, they're just not quite good enough. What else can we think of? Well, what do we use to fuel a car? Gasoline, right? We can see gasoline's even better. There's a reason we use it in cars. It's very, very energy dense. So that could be an interesting target. Gasoline's not bad, but can we do even better than that? It turns out we can. There's a fuel called hydrogen, which is incredibly dense in energy. It's one of the best targets for making a fuel out of sunlight, so that is going to be our goal. We are going to take the sunlight in through our solar panel, and then we're going to store it as a fuel. In particular, we're going to store it as hydrogen. Now, we're going to go back to the periodic table for this because hydrogen, like everything I've been talking about, is a chemical. Now, hydrogen is not next to carbon or silicon. It's way, way over on the other side of the periodic table. It's up there at the top left. Hydrogen is also very, very common. Just like silicon, we can find it in sand. Hydrogen is the most common element in the entire universe. It's what most stars are made of, and that also might give you an idea that it's very, very dense in energy. But it's also what water is mostly made of. Water is made up of 2 hydrogens and 1 oxygen. So if we wanted to have a fuel source, we wanted to have a way to get a whole lot of hydrogen, well, we already have one. We live on a planet that's mostly ocean, mostly water. So we can store lots and lots and lots of energy as hydrogen if we can just get it out of the water. And how do we do that? That is a chemical problem. It turns out that the way you do it is with electricity. So you use electricity to perform a chemical reaction. It's called electrochemistry. So what we're going to do is we're going to take 2 molecules of water. We're going to apply some electricity to it. In this case, it takes about 1.23 volts of electricity. And we're going to split the water into hydrogen and oxygen. Now, you might notice, remember from before that oxygen was really important in that combustion reaction? Well, what we can do here is we can split that water, we get the hydrogen and the oxygen out. We can then do the combustion reaction, put them back together. Remember in our that diagram where we had the amount of energy changing? We can do that combustion reaction and we just get the water back out. So we have a whole cycle that we can do where we can get the water, split it into fuel, recombine it, and then we get the water back out and we can run our cycle again, just using energy from the sun. So this is an idea of how we might be able to make solar fuels, is what we call it, make hydrogen from sunlight. So just like before, we have our semiconductor, we have our car electron down there, and we have the valence band and the conduction band. So just like before, we're going to have our photon come in, hit our electron, which is then going to absorb the energy, and it's going to try to leave that semiconductor again, but this time it's going to get caught. So before, the electron could just move wherever it wanted to, but this time there's water around. And the electron got caught by the water, and if it's got enough energy, it's going to split it apart into hydrogen and oxygen. Now, seems like the problem's solved, but it's not. There's a lot left to do here. So in particular, one of the things that's really important is economics, actually. So chemists have to think about the science, but we're in applied science, so we have to think about how much things cost in the long run. So in order to do this water splitting reaction, we have to have a few other components, and some of those are very expensive. In particular, we do a lot with platinum and iridium, which are very, very rare metals and very, very expensive. It's a lot like gold. Sometimes it's more expensive than gold. So you can imagine if we're going to be building a new world engine that's going to power the entire planet, we're going to need a lot of platinum and a lot of iridium. And that's going to get very expensive very fast. So one of the things that we want to do is make new, what are called catalysts. We want to make new materials that are able to do the same job, but are much more common in the earth and are much, much cheaper. The other big problem is corrosion. So just like you wouldn't like it if your battery fell apart after a couple of minutes, it's not very useful if your solar panel just rips itself apart doing that reaction over and over again. You have to replace it all the time. Now, it's just a thing that we have to deal with when we do construction. And so chemists are working very hard to figure out a way to reduce the amount of corrosion that we have in these solar fuel cells and increase the lifetime of them so we can get more energy out before we have to spend money to put in a new solar panel. Now, it's not just money. We also want to think about new materials. We've been talking about silicon as our candidate for making solar fuels, but it doesn't have to be silicon. There are other semiconductors out there, some we don't even know about. So we need to discover new semiconductors which might be better at absorbing that light or might be better at moving the electrons around. So that's one of the things that I'm working on and one of the things that maybe you'll work on one day. Because remember, we're trying to replace a massive system. We're trying to replace the entire world engine, which really is the energy grid. And the energy grid is everywhere. It's a massive, massive thing. I have got a picture here of the United States, and those lines crisscrossing it are the major parts of the grid. And you can see it's big. So we are working on a very big problem, both metaphorically and literally. So we would really need to work on these challenges, and we could really use your help on that. We can actually do this, so it's not as though this is some incredible idea that no one's ever done and it's very hypothetical. That right there is a video of me doing this reaction in my laboratory. So it's something we can do, where we can make that hydrogen, we can make that oxygen, we can make these fuels. I've got a picture of a big hydrogen burning turbine, so we can eventually use these fuels on a big, big scale. Now, not only could we use it to power the world engine, we might be able to use it to power car engines too. So remember when we looked at that gasoline versus the hydrogen, and the hydrogen was much better at storing that energy? Well, why not fuel cars on hydrogen? If we're gonna be making a lot of it anyway, why not try that? And so that's another area that chemists are looking into, is designing ways to use that fuel in a more compact system like a car. But we can go even further than that. Now, right now, if we think about how rockets work, if we wanted to move a rocket from Earth to Mars or Jupiter or wherever, the way it really works is, imagine I was trying to go home to North Carolina, which is over 2,000 miles away from here. The way that rockets work now, it would be as if I had a gas tank on the top of my car that could get me 2,000 miles all the way home, which is a lot of gas and a very, very big gas tank, which is not very practical, right? How do we actually do it? We have smaller tanks that can get us a few hundred miles, and then we have gas stations where we can fill that tank back up. So that's one of the things that's really, really interesting about solar fuels, is that it doesn't just work on Earth. And remember when I said that hydrogen is the most common element in the universe? We can find it everywhere. So we could imagine a situation where we launch much smaller rockets to, say, the moon, where they can fuel up and then blast off again to get to wherever it is that they want to go. We could have an easier way of moving not only on our planet, but in between planets, which would be very, very exciting. So I hope you've gotten the sense that in this talk today that we have learned a lot about this world engine. We know that the World Engine is about 18 terawatts of power, which is very, very powerful. We know that it's fueled by coal, oil, and natural gas, which have worked great, but we also know that they produce carbon dioxide because of their combustion reaction, which has been harmful to our environment. So to try to change that, we're going to be using silicon as a semiconductor and a solar panel to try to make a new World Engine, which doesn't run on coal, oil, or natural gas, or any carbon at all. Instead, it runs on hydrogen, which is incredibly dense in energy and can be useful all over the world and even in between planets. So with that, I'd just like to thank the Caltech Public Programs for allowing me to do this talk. I'd like to thank my research advisor for teaching me a whole lot of things, and generally, I'd like to thank the people in my life for encouraging me to do science, because this is a fabulous, fabulous job, and I really hope that some of you get to join us one day.
Thank you, Jake, for a most intriguing talk. If you want to ask Jake any questions, you can go to the link on this website. Jake will be responding within 48 hours, and we'll keep this service up for a few weeks after the initial screening. I also want to thank Mitch Aiken and Kitty Cahalan from Caltech's Teaching, Learning, and Outreach Office, as well as Mary Herrera from the Office of Public Programming, and the entire academic media technology team and the team from Event Productions. And thank you to the Caltech Employees Federal Credit Union, the Friends of Beckman Auditorium, and our many sponsors who make these types of programs possible. We look forward to your joining us again for other performing arts events and science lectures, which you can find out about by checking our website, events.caltech.edu. Thank you for joining us.